Hey class, today we're going to continue on with the last section of Chapter 3. It will be Chapter 3, Section 3, Part 2. So in the last section we talked about what is a phase change, what happens to the temperature during phase change, and whether something is going to gain energy or release energy in terms of a phase change. And we use the words endo versus exothermic. So what we're going to do now is kind of discuss these phase changes in a little bit more detail. First, we're going to focus on melting and freezing because they are opposite processes of one another. Our first key question says, how does the arrangement of water molecules change during melting and freezing? And if we remember our states of matter that we learned in Section 1, this is going to change whether it's a solid or a liquid. So it says the arrangement of molecules in water become less orderly as a water melts. And remember, that's because it's going from a solid, which is extremely orderly, to a liquid, which is somewhat orderly. And then it becomes more orderly when water freezes, and that's because it's going from a liquid, which is somewhat orderly, to a solid, which is very orderly. So let's focus a little bit more on melting. Each water molecule contains 2 hydrogen atoms and 1 oxygen atom. We know that because the formula is H2O. In ice, attractions between water molecules keep those molecules in a fixed position. And that's because, remember, ice is a solid. Solids are going to have strong forces of attraction that keep them just vibrating in one spot. Any energy that water molecule gains or that ice gains after a phase change is actually going to increase their kinetic energy because it's going to absorb energy from its surroundings. So as it melts, again, when it goes solid to a liquid, in order for it to go from a fixed position into a position where it can move, it has to gain energy. So when an ice cube is removed from the freezer, heat comes in, it's endothermic, heat comes in from the air. The ice starts to gain that energy or gain that heat, and those molecules start to vibrate more quickly. Eventually, around the melting point of water, which is 0 degrees Celsius or 32 degrees Fahrenheit, some of those molecules are actually going to gain enough energy to overcome that very strong force of attraction and begin to move from their fixed position. And once all those molecules gain enough energy, they are able to kind of move around each other because they are now a liquid and melting is complete. Freezing is going to be the opposite. One of the common misconceptions with freezing is that people often think freezing takes place during very, very cold temperatures. But in fact, remember, freezing is any time that a liquid turns into a solid. So there are a lot of solids at room temperature and they are considered frozen. For example, silicon freezes at about 1,412 degrees Celsius, which, to give a little bit of perspective, is about 2,574 degrees Fahrenheit, which is an extremely high temperature. So any energy removed after the freezing is complete actually decreases the kinetic energy of molecules and the temperature drops. Remember, if you are freezing, you are going from a liquid to a solid. Remember, liquids have enough kinetic energy in order to move around each other, but as they lose that energy, because they are losing temperature, they tend to get very slow and sluggish until they remain at one spot. They lose energy as they go to a solid. So this is just kind of giving the breakdown explanation of what we see when they lose energy. When liquid water is placed in a freezer, energy is actually going to flow out of that water and into the air in the freezer. And what's going to happen is that water cools down. And as that energy leaves it, my average kinetic energy tends to decrease. Those molecules tend to move a lot more slowly. Eventually, at the freezing point of water, again, this is at 0 degrees Celsius, it is the same as the melting point. Some molecules are going to move slow enough that those forces of attraction begin to have a very, very strong effect. Like we stated, solids have a very strong attraction force. And eventually, that attraction force becomes so small, it's going to draw those particles into an orderly fixed arrangement. And that's when we know freezing is complete. The next two processes that we're going to talk about is vaporization and condensation, and these are talked together because, again, just like melting and freezing, they are opposites of one another. Vaporization is a phase change when a substance goes from a liquid into a gas. This is an endothermic process, and remember, endothermic means that it is going to gain heat / energy. And there are two actually types of vaporization processes that you guys are probably heard of or familiar with, and that is evaporization or evaporation and boiling. First, let's kind of focus on what exactly evaporation is. You've probably seen this after a rain shower on a sunny day. You're going to notice that there are puddles of water on the road. But if you come back a few hours later, those puddles are going to be gone because the heat from the sun evaporates that puddle off of the ground. And what evaporation is it actually changes something from a liquid to a gas at temperatures below the boiling point. We know that water boils at about 100 degrees Celsius or 212 degrees Fahrenheit, but on a hot sunny day, it's not 212 degrees Fahrenheit outside, so that is when you see evaporation occur. Say it's only 97. That means that water evaporated or turned into a gas below its boiling point. So a couple things to keep in mind about evaporation is it takes place actually at the surface of a liquid. Only that very, very top layer of liquid molecules are actually absorbing the heat. You can kind of make this analogy to a pool. If you've noticed, the surface of a pool is actually a lot warmer than if you were to go into lower levels of a pool or deeper into the pool. And that's because only the surface is heating up. And so when they heat up, this actually occurs and it turns into a gas at temperatures below the boiling point. Here is a water bath of course, water that birds used to drink out of. And it's going to sit outside, and over time we're going to see that water level tend to decrease. And that's because here all these water molecules on the surface are actually gaining energy from the sun. Eventually, they're going to gain enough energy in order to overcome their forces of attraction, and they're going to turn into a gas. But only the surface level of water molecules are going to be able to do that. All the water molecules underneath are going to stay a liquid. And so then the first layer evaporates, then the next layer evaporates, and then the next layer. And that's why evaporation takes time. It happens over time. One thing to note that when a water evaporates, especially in a closed container, you're going to notice that it tends to collect water vapor or very mist at the very top of it. And this water vapor actually causes a pressure within a closed container. And we have collisions that happen between the molecules of water and the walls of the container. And we tend to call this vapor pressure. Vapor pressure of water actually increases as temperature increases, and at higher temperatures, more water molecules are going to get enough kinetic energy, again, in order to overcome those forces of attraction and turn into a gas. The other type of vaporization is called boiling. As you heat a pot of water, one thing to know is when you heat water, both the temperature and the vapor pressure increase. At about 100 degrees Celsius, molecules below the surface of the liquid are going to start getting kinetic energy. So one of the big differences that we need to notice between vaporization and boiling is vaporization is at the surface. Boiling, notice we're talking about things below the surface, now getting enough energy to overcome that force of attraction. And when it does that, things are going to start turning into a gas. And so water vapor is being produced, and water vapor is actually less dense than liquid, so those bubbles are going to actually quickly rise to the surface. And that's why when we boil something, we see these bubbles get made on the bottom, and they quickly come to the surface. And when they start coming to the surface very rapidly, which we consider the true boiling, this is when vapor pressure is actually about equal to atmospheric pressure. So the temperature, one thing to know is that the temperature at which something boils has to take place at the boiling point, and it also takes place throughout the liquid. Notice it's not just the surface that is turning into a gas. We see bubbles all throughout this container, and again, it happens at the boiling point. One thing to know about the boiling point is it's actually going to depend on your pressure of the atmosphere. So, for example, if you live in Colorado up in the Rocky Mountains, water tends to boil at about a different temperature than if you were at lower levels. So, at higher elevations, the pressure is going to be lower. So, actually, the boiling point's less than 100, even though we always teach you about 100. So I'm going to ask this question, I know for a fact, on your guys' homework, but let's talk about the differences between evaporation versus boiling. And the first thing that we have to realize, the big difference that I said on the last few slides to summarize, is where it takes place. Evaporation takes place on the surface of a liquid. To counteract that, boiling takes place throughout the liquid. So that means both in the surface and below the surface. The other thing to take away from it is at what temperature does this happen? So evaporation takes place below the boiling point, whereas boiling takes place at the boiling point. So things can evaporate below 100 degrees Celsius, but things cannot boil below 100 degrees. It has to actually be that. Condensation, now that we're off vaporization, condensation is going to be the opposite. Instead of going from a liquid to a gas, this is where you're going from a gas to a liquid. And this makes condensation actually an exothermic process. Again, you're going from a gas that has a lot of energy to a liquid that has average kinetic energy, or kind of somewhere in the middle. A good example of condensation that you might be familiar with is if you go outside, you're going to notice that there is going to be some kind of liquid on the grass, and we call that morning dew. That is a good example of where we see things cool down enough, the water in the air, cool down enough that it kind of collects as water on grass. Another example is the shower. When you shower, you heat up that water where it turns into a vapor, and then when it hits something like a mirror, it cools off to cause this little fog on a mirror. Another place where you probably heard condensation is the sides of a glass. If you get a very cool glass of water and you put ice in it, you're going to notice that some of that water is going to collect on the outside of your glass without actually any liquid spilling. And typically what happens is water vapor in the air actually hits the side of that very cool glass, and it causes that temperature in that gas to drop very quickly, and it causes it to lose energy enough to start forming again a dew or a condensation on the outside of your glass. And one thing to know is actually in a refrigerator, these are two very important processes. They keep food cold. Again, those two processes, I know you have blanks on them. The first blank is vaporization, and the second process is condensation. Basically what happens is energy inside that food compartment actually is used to change from something called evaporator, a liquid, and it causes it to change from a liquid to a gas because it's actually taking in the energy from your food that is being released. And then it takes that energy that's released when that compressed gas changes back to a liquid in a condenser. So it's going to take that fluid and take it to a condenser where, again, it causes it to cool down, and that gas changes back to a liquid, and it releases that heat on the bottom of a fridge. If you've ever felt the fridge, you can kind of feel heat being pushed out at the bottom, and that's kind of where your condenser at. Again, this picture actually probably does way more justice than me explaining it. You put things in a freezer, energy from your food gets absorbed into your evaporator. And then there's liquids that run through these coils. And that liquid, again, gains that energy from your food and turns this liquid inside this coil into a gas. That gas then travels down the tube to a compressor, and that compressor takes that gas and turns it back into a liquid. And when it does that, the energy has to go somewhere, and the energy gets released out to your kitchen. Again, if you've ever went by your fridge and heard it running down here, you're going to feel warm air being pushed out because that's the energy that's being released from absorbing from your food to cool it down. The last two opposite processes are sublimation and deposition. And so we're going to first talk about sublimation. If you've ever heard of dry ice is just the frozen form or solid form of carbon dioxide. Carbon dioxide actually doesn't turn into a liquid as temperature increases. It actually goes straight from a solid straight into a gas. There is no liquid phase in between, and when there is no liquid phase in between, we call that sublimation. This is a phase change where it goes from solid into a gas, again, without going to a liquid first. This tends to be an endothermic change, which means it absorbs energy. Again, we go from solids that have very, very little energy straight into a gas, which has a lot of kinetic energy. So it had to get that energy from somewhere, and it absorbs it like most things from its surroundings. So sometimes when dry ice turns into a gas, we say that dry ice sublimes. And again, we see that carbon dioxide vapor being produced in the form of clouds. In fact, here, dry ice subliming is a very good technique to catch mosquitoes because they are actually attracted to carbon dioxide gas. And the last one is deposition. And deposition is going to be defined as whenever a gas changes directly into a solid. So it's skipping that liquid phase again, and we call that deposition. This is actually considered an exothermic process, which means it releases energy. If we think about it, a gas has a lot of energy, and it's going straight to a solid, which doesn't have a lot of energy. It can't really move around. So it had to give off that energy. One of the biggest examples of deposition is when you see frost form on windows, especially on a very, very cold day. What happens is you have water vapor in the air, and it's in its gas form. And then as soon as that water vapor in the air comes in contact with your windshield, which is super, super cold because it's wintertime, it instantly changes into a solid. And that's because that water vapor in the air loses or cools down, loses that energy fast enough that this change in state is direct, gas to a solid without changing into a liquid. Okay. And that's the end of today's lesson. If you have any questions, please make sure that you ask, and I hope you guys have a great day.